Recording is on.
Okay, hey everybody. So last week we discussed about this minimal binary search tree. So given a sorted array, basically array has all increasing elements and write an algorithm to create a binary search tree with a minimal height. So this is what we discussed last time. Basically, array will be given and we need to create a binary search tree. So this we solved it. Now we are going to look into the another problem. Given a binary tree in an array, this is all similar to this one. So sorted elements increasing order, which is also same thing here. Given a binary tree in an array, but here it is not a binary search tree. That's the difference. Just a binary tree in a form of array, and write a binary tree traversal algorithms. So pre-order, in order, all those things without even creating a tree data structure. So we have to. This is a kind of algorithm we need to understand before going to the heap. The heap is very important concept. So in order to understand how the heap is working, heap also called the priority queues in many of the other languages. So before going into that, we need to understand how to represent entire binary tree in an array, simple array. That's why I put this problem before heap. So let's dive into this and understand. And Okay, and before diving in, I just want to make sure we have some basics sorted out. So Vinil, I think you have some understanding. Do you have understanding about the binary tree versus binary search tree? Do you want me to give any introduction?
No, carry on. But I attended few classes like binary search of yours, so
Yeah.
I'm able to understand those things.
Yeah. So basically, the binary search tree has a simple difference in terms of the um, rule, right? When you are creating a binary search tree, so can you explain what you remember about binary search tree?
It's a order of search, something like left to right.
Hmm. So let's
Um,
say we have a tree like this. One, two, three. Is it binary search tree or which one is binary search tree here? Both are binary trees, right?
yes.
Binary tree means, yeah, go ahead. Which one?
The second one is the binary search.
Exactly. So the left node, the value of left node should be less than or equal to the root node value, and the value of any of the right children, right subtree should be greater than the root value. So this is binary search tree, BST. This is just a binary tree. Binary tree means like which has max two children, right? So this is not binary tree. Let's say we have A, B, C, D. So this is just a tree. This is just a tree. So it can have many multiple branches, and this is a binary tree that where every branch, every node has maximum two nodes. It can have maybe one node like this. This is also binary tree.
Yeah.
But binary search tree is also a binary tree, but there is a special condition here, right? So heap is also binary tree. Heap has heap also. I think heap is binary tree. Yeah, not binary search tree. Heap is like binary tree has a special condition. We will discuss that. So now, how can we represent this binary tree, this particular binary tree, in an array format? Okay, that's what we are going to discuss. So here is the where is that? Yeah, let's go here. Okay, so we can think of like this. So this is a different problem. This is a little complicated. It's a binary tree array implementation. So let's assume that we are not implementing it. It's already there. So let's say this is array. This is a binary tree we have. Okay, A, B, C, D, E, and F. So if you look at this, how many elements? Let's say maximum number of elements in this tree. So we have something like this, right? So let me clear. We have A, B, C, D, E, and then look at that. Only F is here. Only F to the right of the C, right? So here is the F. So, but if it is a balanced binary tree, like balanced means like it's almost equal, right? So it is a balanced binary tree, but there is one element missing here, right? So maximum, at a maximum, you can have one more. There is, yeah, before F there could be one more element here, because there is no left node for C. You can put it there, or otherwise there is no element here. But how many elements? What is the maximum number of elements until F? So 1, 2, 3,
7.
4, 5, 6, 7, right?
7.
So this is maximum 7. So that means in order to represent this in an array, what you can do is, of course, there is a no element here. There is no element here. But in order to represent this whole 7 elements in a simple array, so we can do that. So how that can be possible? So if the elements are putting in a level by level order, if you look at that, A is at 0 and B and C at 1, 2, and 3, 4, 5, 6. Just a sequence. If the elements are like this in a simple array with a level by level sequence, okay, we have A here, and the next level is BC, right? B and C. Next to D, E, and here is the thing. So either it is just an empty cell here and F here, right? So if you look at here, 0, 1, 2, 3, 4, 5, 6, right? So 7 elements means the index will go all the way to 0 to 6, right? If you have n elements is the maximum number of elements in the array. So that means the index will go from 0 to n minus 1, right? So here is maximum number of elements until F is 7 elements, because of course you can add tails to D, E, F also, but they are clearly saying F is the last element. Okay, if F is the last element, there could be maximum 7 elements. Of course, we have only 6 elements here, but there could be 7 elements. So they are putting in an array. Okay, so this is the array representation of the whole tree. So it's just level by level, but there is no element here. You can think of, let's say these are all characters, not the objects. You can think of as a characters. This is empty character at the level at the position 5. Okay. Now this is not the input. Now this is the input. So the algorithm here is given the, let's look at the problem again. Given a binary tree in an array, we have an array. Now we need to write binary tree traversal algorithms. I think we already know what is pre-order, what is in order, post order. Everybody knows that, right? And there is one more important called path to the parent, which is really important for the heap. In order to understand heap or priority queue, this is very important. So let's dive into these 4. So how can we do this traversal in the array itself without creating array data structure? So basically, we already have an array. We are not going to create a node and left and right like this. We are not going to create separate data structure. How can we do the same? How can we utilize this array to print the in order, pre-order, post order? So let's look at the algorithm here. Let's put the indexes also here: 0, 1, 2, 3, 4, and 5 is null, and 6 is here, right? So now let's can anyone tell what is the pre-order for this? Is it pre-order? Let's start with pre-order. Yes. What is the pre-order of this tree? Arvind or anybody? Karnya.
Pre-order is root, left and right. So
Yes. Node, left, right. Basically, first we need to print the node. Okay. And then you have to go to the left side and right side. Okay. Then what is the pre-order for this given tree?
A, B, D, and E,
A, D, E,
and then CF.
C, F. Yes, that's good. So now, how can we print this? Basically, I am giving this input A, B, C, D, something like just a normal, array is given. Now, how can we print this format? Okay. It goes to A, and then it goes to B, and then it has to go to D, and then right E, and then it needs to come back to the C, and then go back to the F. So what is the logic behind it? So basically, if you are looking at the tree level, right, we are traversing the route, and then we are finding what is the left node, and we are going to the left, and we are printing the route again. And before printing C, we don't want to go A, B, C, D, right? Now at the point of B, what are we doing? At the point of A, after printing, we are finding the children, we are finding the left children, and printing processing it again. At the point of B, we are printing B, and we are trying to find the left children of B. Okay, so if you look at carefully, what is the formula here? So there is a formula where you can go and get the children. Okay, so
Suresh,
yeah,
we have done predecessor and successor in a problem, right? Will that format help here?
pre-successor, you mean like
Predecessor, successor, yeah.
what is that one?
Yeah,
Oh,
finding the previous element in an array and the
finding
successor.
the, yeah, oh, successor. Okay, common successor. Yeah, it may not helpful because you're thinking about. I think you are asking about find in order successor, right?
Yeah, yeah, yeah.
Yeah, in order successor. How we do it? Yeah, that's in order successor. Basically, we need to find the next element. Yeah, this is in order successor. Correct. So we are working on, but this is not in order, right? We are working on pre-order. We are working on pre-order. Of course, you can think of as a pre-order successor. So A, if you printed A and you printed B, what is the pre-order successor? That means in the pre-order, what is the next element? So after B, it has to go to D, right? So what is the formula? Here is a formula they have given. So we need to. This is different. So I can easily write here. So it's the same formula. It's given in a different way. So it's okay. I can tell you. So how to derive left node? How to derive right node? Okay, at any point of time, let's say you are at, let's say it is the thing really big. Let's say this has 1,000 elements. Okay, so now see, if you look at here, see b left node is here D, and B right node is here E, right? So there could be many nodes between, right? See, if you look at C right node, there is no right node here, but C left node is F here, right? So there could be multiple elements between those. So let's say you are at here. So you are at N here, okay? No, you can think of N is N 0 to N minus 1, right? So let's say you are at K. This is K, index K, okay? Now you want to know the left children of this one. There could be somewhere here, and right children there could be somewhere there in the big array, right? How to find that index? How to find the left children, and how to find the right children? Okay, so left children equal to 2k plus 1, and right children equal to 2k plus 2. That is the formula. If you apply this formula, so basically that this will give you the index of the left children, and this will give you the index of the right children. Okay, so now we can test it. Okay, so now you are at 0, right? K equal to 0. So let's figure out for the A. You printed A, and K equal to 0, and what is the left children? 2 into 0 plus 1. Just apply the same formula, right? K equal to 0. That means what is this one? 1, right? And what is the right children? 2 into K, 2 into 0 plus 2, which is equal to 2, which is the right children, right? The same formula applies for any index. So now let's say you printed A, you found left children and right children, and you found left children B, and you printed B. Okay, now you are at the index 1. So B is at the index 1, right? So now K equal to 1. So now you printed B. Now you need to find left children and right children. So left children equal to 2 into 1 plus 1. That is left children. And right children equal to 2 into k equal to 1 plus 2. So what happens here? 3, right? 2 into 1 is 2 and 3. So left children is at the 3, index 3. So if you are at 2, if you are at 1, if you are at B location, so you will find the left children by using this formula. So that means left children is D, right? And now right children is 2 into 1 plus 2, 4, right? So that is the right children. Got it? Is it clear
Yeah.
to everybody?
Yeah.
So at any point in the array, you can easily find the left children and right children. So the basic idea here is very simple. The reason it is easy is they are putting an empty string here. If they are not putting empty string, that is whole lot of hell. Because if the f is here, right, then it will be the left children of, it will be like this. F will be here. Because what happens, like c equal to 2, right? Index of c is 2. K equal to 2. Now you printed C. Now you need to find the left children. Like 2. So left equal to 2 into 2 plus 1, which is 5. This is 5, right? Index 5. So now right children equal to 2 into 2 plus 2, which is 6. So at the 5, you have an empty space. If you are putting F here, then that will be the left children of C. But we are not putting F here. We are putting just an empty space. So there is no element. There is no left children for C. So that's why there is an empty space. Now, right children is there, which is at the 6 we have F. Right? Is it clear to everybody how to calculate the left children and right children?
One question, Suresh.
Yes.
So, if there is a gap, then we cannot find using this formula, right?
Gap means the 5, right? This is the
Yeah.
there is a gap. There is no element here, right?
Mm-hmm.
So what we will do is it's kind of null condition. So if you find an element, like you got 5 here, but there is no element at 5, so you will check whether this is an empty space. If it is empty space, okay, you no need to print, you no need to process. It's just like you can treat that as a null in the normal. If you are putting in a normal right node, left node data structure, right? So that left node is null. There is the c dot left equal to null, right? And c dot right equal to f.
Mm.
So we can think of that way. So when we are writing this in order, pre-order, post-order, whatever the order, so that is the situation. So we should not process anymore if you encounter an empty space. Okay. Similarly, let's apply this rule to the leaf nodes also, because that is another thing, like how the algorithm works. It will print A, and then we'll print B, and then we'll print D, right? A, B, D. Now, before going to the E, what we do, we will check whether if there is any left nodes or right nodes for D, right? That's how the pre-order works. So now your k equal to 3. What happens to the left node? 3 into 2 plus 1. That means 7, index 7. And what is the right node? 3 into 2 plus 2, which is 8. So 7 and 8. So these are the indexes we got. Do we have any elements? Do we have any 7 here? No. Do we like index 7? No. Do we have any index 8 in the array? No. So they already gave what is the maximum number of elements. Basically, array has only 7 elements, 0 to 6. So we already know how many elements in the array and what is n. We already know n. So now what we will do is we will stop if the index is greater than n. So here is the n 0 to n minus 1, right? So n equal to 7. So or n minus 1. Let's look at this one. So 0 to n minus 1 means 6. So these are the only valid indices. 0 to 6 is only valid. If you are calculating left or right, which is beyond these numbers, either it could be the minus values are not valid, or greater than 6 is not valid, because there are no more elements in those in those indices. Okay, that is another stopping condition for the recursion. There are two stopping conditions, right? One is if you find an empty cell. Empty cell means the one which doesn't have any value, any character. And the other condition here is if you are the indexes, if the calculations are going beyond the size of the array. Is it clear to everybody, or is it any confusions here?
Clear.
Right?
Small
Yeah,
question that, for
sure.
example, if there is any problem like this, so will they give the indexes, or like how the question will be something in a problematical way?
In a given way, if you look at the question is like this, right? Basically, we are giving an array, um, given a binary tree in an array. So in an array means you already know, like array means you can easily calculate length of the array,
Yes.
correct?
Yes.
So even though let's say here we have only 7, but even though let's say they gave array of 100 elements, but rest of the elements are empty, right? They have values only until 6. Rest of the elements are initialized with whatever the value. If you are taking any integer array, the default value is 0. If you are taking a string array, default value is empty string,
Okay.
right? If you are taking an objects array with employee objects, let's say this is 100, I'm creating a company, I'm creating a data structure array for all the company employees, and each value has an employee object. So I recruited only six employees only until now. I recruited 6 employees, and here is the structure. A is the boss, and B, C, and C are the subordinates, and C is having another subordinate, right side subordinate, no left side. So at this point, but I initialized the array with 100. So whenever you initialize it with 100, every object is null. By default, the what is the default value of object is null, right? So in that
Yes.
situation, you need to check with the null value. If any null value is there, ignore. Otherwise, process it. So this is the given. This is the given array. So given an array, write the algorithm. So by using this particular array means it already gives you what is the length of the array. They no need to tell you how many elements of the array. We can calculate ourselves, right?
Okay. Thank you.
Is that clear?
Yes. Yes.
Yeah. So this is the way to navigate. So these particular formulas are really important to understand. So this will enable you to navigate without even creating data structure, without even creating separate tree data structure. Okay, here is the thing. So here is, they say like father equal to p. Father means the parent. Okay, then left son equal to 2 into p. Oh, this is a different formula. I think this is the one we need to follow. So if the elements are 0 to n minus 1, that's how the array will work, right? Array index starts with 0 and array index ends with n minus 1. So father equal to p and left son equal to 2 into p plus 1 and right son equal to 2 into p plus 2. They are not giving any daughters. I have 2 daughters. How can I say like that? They are not putting daughters here. They should say like left daughter, right daughter. So anyway, so that's just the representation of left children and right children. Okay, this is the formula to calculate in an array. So now let's dive into the algorithm and see how to. Now you understand. It's very easy to look at the algorithm and process it, right?
Yeah.
So I can go ahead and show you the algorithm. So is it clear to everybody? Karanya, is it clear to you?
Yes, Suresh. Yeah.
So we'll also discuss about the last algorithm, the path to the parent, but let's discuss about this one first. So I created this array just as I discussed here. And if you look at here, I initialized with the values directly, and look at the value here, empty space. Okay. So now they have a clear array with 7 elements. Of course, one element is empty, which is kind of null. So now we need to print in order, pre-order, in order, post order. Okay. So I'm going to show you the first print pre-order. Okay, how can we do this? We know that in order to start any of the traversal, what we need to start from the root, correct? So this is the binary tree given in the character array format, and we are just declaring like a new line and pre-order equal to, and binary tree, we are passing the binary tree, and we also sending the index of the root. In a normal data structure, what we do, we will just send the root reference to the root, which is pointer to the root. But this is not a pointer data structure. This is just an array. So that's why we are sending the array, and we also sending the index. Okay, let's look at it. This is the actual algorithm. This is the actual algorithm where it will do the recursion. So simple. Binary tree. Here is a binary tree, and here is the node index. It could be node, means it could be root, it could be any node. So here is the index. Now I'm just checking tree max size. What is the tree max size? So it is very easy, right? So we can easily get the length, binary tree dot length. Now, if index is either less than 0 for any reason, if the index becomes minus, or index is greater than tree size minus 1. So the maximum is 0, 10, minus 1, right? So index going out of the tree. Basically, you are trying to print something which is not a valid index in the binary tree. So basically, you are reaching a null children, right? So that's kind of thing. So in that situation, you just return. This is one base condition, and another base condition here is empty children. If the binary tree node dot index, that particular index, then the value here is just an empty string. It's not a valid children. There is no value to print, and there is no need to process anymore, right? That is return. If either of these conditions are false, that means this is a valid index and there is some value in that particular index, correct? There is a value. Just print the value, because we are in a pre-order. Pre-order means we need to print the node. Now you need to process the same thing for left child. So how to get the left child? Simple. As I said before, node index into 2 plus 1, and node index into 2 plus 2. That is for the right children. So you are calling the same method, which is recursion, where you are sending the process, you are asking to process the left children, and you are asking to process the right children. Is it clear?
Yes.
It will take care of every condition, every situation. So even if you are at the index which is at the D, if you are at the D, what happens? The left children is 7 and right children is 7. Both are out of indexes. So the maximum size is 0 to 6, right? So we already calculated it. So only goes 0 to 6. So both are out of indexes. That simply it will return. Otherwise, it will calculate the and return and print.
Suresh, suppose we have that one child is missing of a particular node. So for that case, shouldn't every every node coming after that node be shifted by one, or it will be taken care of?
Look at the array here, right? So here is so the given array has an empty value in it. It's not like you are putting f here, right? So if you look at the given array, it's an empty value here. So you don't need to shift anything, right?
Okay.
So
Yeah.
look at the formula here. At 0 you have A. So at 1 and 2 you have B and C, right? At index 3, 4, 5, 6. This is 3, this is 4, and this is 5 and 6. So if you calculate the left children for 2, right? 2 into 2 plus 1, which is 5, you got the empty children. Once you have empty children, there is no more children available. So you cannot put children for empty node, right? Unless you put something here, you cannot even have any children for this.
Got it.
So we can stop here. Once you get the empty, you can stop. That's why that's another condition. So blocking condition or return condition. Otherwise, you can go to the next node. So the f will be calculated from the c itself, because 2 into 2 plus 2, which is 6, right? So from f you will get to the from c you will get to the f by using the formula. So none of the nodes will be missed. For sure, I am clearly, as long as the binary tree is correctly given. If they gave a children for empty node, then definitely you cannot reach that. Let's say you have G and H here, which is how they can. So you can put in the big array, you can put G and H somewhere in the array, but you cannot reach there because there is no parent for G or H here. Correct? So as long as the array was given in a proper way, we can definitely reach every node in the tree. So the array was given in a proper way. That is, we no need to worry about that.
Suresh, the
Yeah.
tree is well balanced here, right?
Yes,
What if the tree is unbalanced?
that's a good question. So let's say this is the tree, right? Let me remove and redraw again. It's so much here. So you have A, B, C, D, E, and we have F. It's almost balanced. So now this is at 0, 1, 2, 3, 4, and 5. There is nothing, and 6 is here. Okay, 0 to 6. The array has 0 to 6. Now, do you want to create any children for E or D? Will let me know. So let's create a children for one
E.
of these elements. Okay, E, left or right?
Left.
Left. Okay, and what is the value there?
H.
Okay, okay, now you need to insert this in the array. So array is like this. This is what I'm just trying to explain. So in order to, so if you want to insert H, you have to insert at the correct position like this. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. You have something like this. So now you need to put A here, B, C, D, E, F. We should not put at 5. We have to put F here. So now where are you going to put H? It has to go to the, so this is index 5, index 6, and there will be 2 indexes for, at any point you can add left and right for D. So it will be at 7, this will be at 8, this will be at 9. So you need to add H at 9 here. If you add H there, then that is the left children of E. So let's calculate. So 4 into 2 plus 1. What happens? 9, right? So to put the H at the correct location, you need to calculate the left. What is the left index? So if you want to put H at the left, you need to put at this location. So at 9, if you put H here, then that is connected as a left node of E. Is it clear?
Yes.
So that's how the tree you need to build. So if you really want to put H as a left node of E, you need to create an array of 10 elements and put the H there. And 7 and 8 are reserved. 7 and 8 are reserved for the left and right of D. Right? If you calculate D is at the 3. So 3 into 2 plus 1, which is 7. 3 into 2 plus 2, which is 8. So these 2 indices are reserved for the left and right nodes of D. So you should not put anything there unless you want to insert anything for D and left or right for D. Otherwise, you need to make that space. I know this is not an efficient because you're unnecessarily wasting the spaces. But of course, we are not wasting, because I'm creating a company with 10 employees. D is just an employee. He is just a programmer. He is not a manager. Let's say the D became a manager, he got another 1 or 2 recruiters, like 2 programmers, then there will be 2 child nodes. Unless he became manager, his child nodes are empty. Got it? So this way I can represent the whole binary tree in an array format. If it is clear, we can go to the next one. So here is it is simple. It's the same thing for Inorder and post order as well. I will send the algorithm. It's just a simple matter of exchanging or changing the sentences here, right? So let's look at the post order. Okay, yeah, in order. Let's look at the in order. In order also same thing. Okay, we are sending the root index, and in order means left root right, left node right. So you should not print it. The same conditions. These are all same conditions. So only thing is we are processing the left child and then printing the node and processing the right child. Just the statements will will move. That's it. Same thing for post order. What is the post order?
Left, right, and root.
Yeah. So left, right, and then node. So just process the left node, process the left child, and process the right child, and then print the actual element here, binary tree of node index. So I'm just putting a space here so that you can look at the values. So I can run without debugging and show you. So we just calculated the pre-order, right? Let's look at here is the input given. And let's look at the pre-order, post-order, and in-order. Come on, it's building simple algorithm. View output. Okay, now we got it. Okay, so look at this. So pre-order, right? A, B, and D, E, C, F. And look at the in-order. In-order is always starts with the left node, right? So it gone all the way to D, B, E, A, C, F, which is right? And the next one is post order. Look at that. D, E, B, F, C, A. Finally, the root node. Okay. Is it clear? So now let's look at the other algorithm, the last one, which is also important. Print path to the parent. So since it is an array, you can not only you can navigate to the child, you can also navigate back to the parent. Correct? So in a normal data structure, you cannot navigate from here to here. You cannot navigate from child to the parent, right? Unless you have a parent reference or parent pointer. So you can always have node dot right and node dot left. If you have node, you will have node and left and right. You can easily navigate down, but how you cannot navigate up unless you have the parent reference in each node. But here it is an array. By using the same calculation, similar calculations, you can go back from children to the parent. So what is the formula to go from here to here or here to here? Can anyone guess that?
So in this,
So
4 into 4 is the value that we need to find. 4 is
no,
equal to
no. I'm giving. You are at 4. You are at E, and I want to know the parent. Of course, we want to print like this. At any if I'm giving an array, and I want to print the path to the parent. So if I give E, what is the path to the parent? E,
child
B.
minus 1 divided by 2.
Exactly. That is the formula. So basically, the index of the child minus 1 divided by 2. So 4 is in. So you are at 4. So I said start at E and tell me all the parents. So start at E, 4. Index equal to 4. And the formula here is parent equal to child index minus 1 divided by 2. So what is the child index here? 4. 4 minus 1 divided by 2, which is 3 minus 3 by 2 is equal to 1. Basically, you will take only the integer part. This is integer division. We don't need any decimals, right? So now we got 1. So that is, again, so let's calculate from the parent 1 b to a. So the same thing, right? What is the index of b? 1 minus 1 by 2, which is 0 by 2 equal to 0. So that is the parent. Does it work for D also? Let's look at that. So D is 3, right? 3 minus 1 by 2, which is 2 by 2, which is 1. See, even 4, you are getting 1. Even if you start at 3, you are getting 1. Is it clear to everybody that this algorithm, this finding the parent?
Yes.
You can also check with H. So H is 9, right? 9 minus 1 by 2, which is 8 by 2, which is equal to 4. So that's where the E is, right? So if you look at here, 9, it goes all the way to 4. Now, again, apply the same formula. 4 minus 1 by 2, which is 1. So from 4, it will go to the B. And B, it will go to the A. This is how you navigate. So if I ask you to print the path from H all the way to the parent, so you can print H, E, B, A. You can print all this whole path. Is it clear, Karanya?
Yes, Suresh.
Let's go ahead and look at that. It's very simple. So once you identify the algorithm, so this is the path to the parent from E, path to the parent from F. So I'm just sending that. So basically, this algorithm needs two things. Again, the same thing: binary search, the actual binary tree, and also where do you want me to start? This is what. So if you want to start at E, what is the location of E? 0, 1, 2, 3, 4. So you're starting at 4. So if you start at E, we need to see E, B, A. And if you start with F, right? So F means FCA. It has to print like, so index of F is 6, right? Now if you start with C, just 2, CA, it has to print just C and A. Now let's start with an empty node. Just somebody is trying like, okay, path to the parent from an empty node 5. So you are saying at 5. So of course, if you calculate 5, then what is the parent? 5 minus 1 by 2, which is C and A. So empty space C and A, but empty space is not a valid node. You can just print an error statement or error message. So that's what we are going to do here. So let me show you the algorithm, which is also pretty simple. Okay, here is algorithm, path to the parent. Okay, so here is the binary tree and here is the node index. This is where you are starting. Okay, so this is also same recursive because you are going same algorithm, right? Same formula applies to each and every node. So what are we doing here? First one is maximum. Okay, there is one more problem here. Let's say, yeah, so if we start at, what is the final condition? The final condition means the stopping condition. Let's say you are at node A, right? So you are at node A. Node A means 0. You need to stop at 0 because there is no node, there is no parent for A, right? So if you apply the same formula, what will happen? Let's see. What is the parent of A? So you are at node n equal to 0 and parent of node equal to same formula. And like what is the formula you just had it, right? N minus, let's say k. I don't want to take n here. So k minus 1 by 2, right? So 0 minus 1 by 2, which is minus value. So here is a minus value. When you have minus value, you should stop. So minus 1 by 2, right? So we need to stop once you reach the minus value because there is nothing, there is no node above A. There is nothing. You cannot go beyond the array of beyond the index of the array, right? Similarly, if they gave something like, okay, there are 0 to 9, only 10 elements. Okay, now if I ask you to print a path to the parent starting at 15, index 15. What is index 15? There is no 15 there. Only you gave only 0 to 9, only 10 employees, and you're asking me to print from 15. So same thing. This is going beyond the size of the array, and here also -1 is going beyond the size of the array, right? That's the condition here. Same condition we had before. So tree max size, and if the index is less than 0, or index is greater than the index of the thing, index going out of the tree, just return. At the same time, if the given index is empty, so given index is empty, you are asking me to start from an empty, so can't start from an empty node. Okay, now this is a valid. If none of these conditions are true, that means there is a valid character at this location. Let's print that, and then let's look at the index -1 is less than 0. This is what we are doing. So as I said before, if you are at the root, right, you are getting minus value. So if there is a minus value here, there is no need to calculate the parent, right? You're already at the root level. So that's what I'm putting here. If the index -1 is less than 0, just return. That means you reached. You can simply say we reached the root of the tree. So we printed the root, simply return. Otherwise, this is not -1. Otherwise, we need to calculate the parent. Parent equal to root index -1 divided by 2. And if the parent is greater than or equal to 0, just do this. Okay. I think wait, do we need to do this condition here? I don't think we need. So because we are checking that condition here anyway, right? Any situation where the parent greater than 0 or parent less than 0, I think this is not required because we are already checking this condition here. One -1, no. I think greater than or equal to 0. Yeah, I think we don't need.
Yeah,
to
I
do
think
it.
we can directly call
Yeah.
that function.
Yeah, let's run this. I wrote this last night. So we got the parent and run the parent. So if the parent is between these two indices, we are processing. Beyond these indices, we are anyway returning it. And if not, we are taking care. So look at this. Yeah. So we started with E. So EBA, right? EBA. And if you started with F, FCA. If you start from C, CA. And if you start from empty node, which is like 5, I'm just sending 5. So it starts with 5. You simply return the error message saying can't start from an empty node. That's it. Is it clear to everybody?
Yes.
This algorithm? Yeah.
Yes.
So it's simple. Maybe there could be little complex algorithms, a lot of complex algorithms out of this structure, but we need to understand how to navigate a binary tree in a given array. Okay, this is not a binary search tree, by the way. So we are just ABCD or any objects so lined up in a proper way. So let's look at the related. There are a lot of related algorithms in the Geek for Geeks. So here is a binary implementation. This is a binary tree implementation. Basically, given a tree that represents a tree in such a way that array indices are values. So they are just explaining this. So this algorithm is basically asking, to insert an element. So let's say if you want to insert some element as a left node of C, how do you do that? Basically, calculate the children and then put the element there. So set the right element C at index 0 and let's set left index D. So it's kind of it's a creating the elements. Basically, this particular algorithm is creating the elements on the fly. So set left, set right. So let's go through this. You can also, I will send this link too. It's very just simple. Like if you are setting the left node, what you need to do. So you want to insert this key as a left node of this one. Just calculate the left. This is the root into 2 plus 1. This is the left node, and you put it there, right? Same thing. If you want to set this particular value as a right node of this node, the right node means root into 2 plus 2. This is the right child, and you put the value there. If the root value is null, so you cannot put anything. You cannot set child, because there is no parent. If you are giving the value at that particular location is null, so you cannot put a value children for that null, right? So that is the another condition they are putting. And a printing tree. So here they are just printing sequentially, right? It's not in order. It's a level by level order. If you are printing like this, what is this? This is just level by level order, right? Just like you're printing as given A, B, C, D. This is level by level. You are tackling one level and you are printing in the next level. So that's what, if you go one by one in the elements, you are going level by level, right? So that's what they are printing that. So, and there is one more complex here algorithm. Construct binary tree from a given parent array representation. So this is also a little tricky. So I will send the link. You go through this if you are interested. So yeah, this is another interesting. So check if a given array can represent the pre-order traversal of a binary search tree. So this is a pre-order traversal. It's a tricky questions. These are not aligned with what we discussed. If you look at here 2 4 3, so like this 2 4 3, this is true, because if you are ordering pre-order, right? Pre-order means root and then root again and then left. So it could be a pre-order. So here, if you look at here, this is not the way we represent it. If we want to represent this tree, right, we need to have one here. There will be one left node here, 1 2 3 and 4 5 6, around 6 elements we need to put. But here they are just putting 3 elements. That means they are not putting empty nodes basically. So it is critical. It is a little bit complex algorithm. And look at this one, 2 4 1. This is not at all a particular Inorder traversal. So check if the given array represents Inorder. Basically, they gave the Inorder traversal. They gave this, we already printed here, right? If you print in Inorder, that is what we got. This is not the given array. So in this algorithm, the input is the actual pre-order of a binary tree. Now we need to check whether that is a proper pre-order or not. So this is a proper pre-order, but this is not a proper pre-order. So given array cannot represent the pre-order traversal of a binary search tree. So it never be like this. There is a lot of discussion here. You can also go through this. These are all a little bit complex questions on this concept of representing a binary tree in an array format. This is a binary search tree, of course. Pre-order in a binary search tree, because that needs to follow this condition, right? The binary search tree condition. We need to check that binary search tree condition here. Okay, so that is the main concept of representing in an array. Now let's talk about the heaps. What is heaps? What is priority queues, and how this work? This is also really big concept. So there are a lot of questions around heap. So in big companies, they don't say use heap, but some of the algorithms can be solved if you use heap. Heap also called priority queue. So I will discuss those algorithms. Now let's look at what is heap and how this works. So you guys know about this popular website, C# Corner is a really good website. So binary heap is a binary tree with some special properties. What is the special properties? Is heap properties are min heap, max heap. So parent node value is less than children node value. That is a simple, definition of heap. So if you look at any parent, that should be less than its children. So again, max heap. Max heap means parent node value is greater than child node values. That's it. So it never there is no relation between the other two values. So let's look at here. So 3, this is the min heap. Is 3 less than the other two nodes? So 10 here, 15 here. So it's 3, which is good. Again, if you 10 here, the next node is 25. So if you are going down in the children, you will get bigger numbers. That is a min heap. Min heap is basically that at the top of the tree you will find small numbers. So at the first level you will find smallest number, and the next level there will be another small numbers. If you are going down in the different levels, you will find bigger numbers. Okay, so now look at here. Max heap. Max heap is the reverse of the min heap. Basically, at the top of the tree, you will find the maximum number. There won't be any number greater than 50 in this tree. If you have anything 51 or 55 or 60 somewhere in the tree, if you added 60 as a child of 45, then definitely that is not a max heap. It's not following the definition, right? So similarly, like BST, binary search tree has some value kind of properties. Similarly, heap has max heap or min heap also has its own property. So we need to make sure when you're adding an element, when you're removing an element, it has to satisfy that condition all the times. Okay, so just basically you can think of this as a tree data structure with a maximum nodes on the top is max heap, and minimum node on the top is a min heap. Not only just that, every node, it's not only just top node or root node, it has to satisfy the every node. So why do we need binary heap? So let's consider the array data structure example when we want to insert an element inside. So why we need this? He is clearly explaining what is the value of inserting. So let's look at the data structure, array data structure. We don't want any trees. Let's look at array data structure. We want to insert an element inside sorted array. We need to find max min elements and insert a proper position. So the problem here is you want to maintain the, let's say, the employees of the company. You want to maintain the employees of the company with their salaries. First, when I ask you, just I want the minimum, the employee with minimum salary. What do? If you are putting an array, right, you need to scan the entire array, and you need to find the element. Let's say you have employees of 1,000 people. So you need to compare where is the smallest element, and you need to find, hey, this is the employee with smallest salary. Let's say you inserted one more. Like if you can do that. Otherwise, what you can do is you can put all the elements in a sorting order. Here is the smallest. Let's say this guy has 100K, and this guy has 200K, and this one has 250K. So now like this, you can put all this. Now whenever an employee joined with 225K, here is the salary. What you need to do? You need to insert between these two guys, right? So if you are putting all elements all the time sorted, whenever you are putting a new element, you need to shuffle all these elements. Otherwise, if you are putting everything in a normal, like if you are adding this employee at the end of the array, the problem is finding the problem. If you want to find the smallest, you need to scan all the elements and find the smallest. So if the insertion is fast, if you are just inserting at the end of the array, the retrieval takes time. Because if you are keep on asking, hey, give me the small number, give me the small number, give me the next small number, every time if you're asking a number, the retrieval takes a lot of time. You need to compare and traverse all the elements in the array, and that takes time. But if you are putting everything in a sorted order, let's say every time, always, okay, you want small, take it. If you want next small, take it. So you can very easy. You can go to in a sequential way, you can go and you can give the numbers. But the problem here is insertion and deletion. Let's say so this employee resigned. You need to shuffle all the elements because we don't want to waste this memory, right? We don't want to waste that memory forever. This employee already resigned from the company. So you need to shuffle these elements into this location. then it will be easy for you to maintain and you can easily retrieve. That's what they are explaining. So that is a problem of using array for this particular requirement. So let's consider array data structure as an example. When we want to insert an element inside the sorted array, we need to find min-max elements of the insertion in a proper position. As I said, what is the minimum, what is the maximum? So as I said, if you want to insert an employee with 225K, you need to find between these two numbers. You need to find this and you need to find this, and then you need to insert at that location and you need to shuffle rest of the elements. We also need to make sure that the inserted new element will not affect the current element or size of the array. That is another problem, right? If you are taking array with initially with 100 employees, let's say you are recruiting another 10, another 20 employees, you need to increase the size of the data structure, which is not possible with array, right? This implementation takes order of log n time for small array size. In the worst case, order of n time. In the worst case, what happens? You need to find all the way to the last element and then insert there. So order of n. Sometimes insertion takes a lot of time. Let's consider one more example. We need to insert an element in a linked list. Let's say, why do you need to go for array? Why we have linked list, right? We can use linked list. As you already aware, insertion in linked list will order of n time. And also we need to make sure new element is inserted in the proper position. The same problem with the linked list. Of course, you no need to shuffle the elements. If you are removing, if you are adding element or if you are removing, you no need to shuffle rest of the elements. What you need to do is just changing the links, right? How the linked list work. This links to this one, this links to this one, this links to this one. So if you want to insert here another node, let's say you want to insert node, so we'll cancel this link and we will link to this new element, and then we will link to this new element. That's it. Now in a proper order. It's easy to insert, but the problem here is, again, if you want to insert at the end of the array, you recruited an employee who is maximum salary than any person. You need to compare with every element and find out. You need to insert at the end, and then here is a new employee will be added at the end. So worst case, order of n again. If you have million elements, in the worst case, you need to traverse, you need to compare with every element in order to add the new element. Okay, retrieval part is okay. You can simply get the minimum here and the next minimum is here, next minimum is here. Retrieval, you made the retrieval easy, but you made the insertion complex. So we are finding a data structure where both will be relatively easy. Insertion, retrieval is order of 1 or order of, we want to find order of 1. What is the minimum? Simple. Take it, root. So that's the main purpose here is, that's right, minimum. Let's say min heap. You want to find the employee with minimum salary. Okay. Here is the root. Take it. Very simple. Order of 1. You are not processing anything because that is at the top. Retrieval is very easy. But how about insertion? Insertion is also comparatively easy. If you compare with array is taking worst case is order of n, and even linked list is also taking order of n. But let's look at this one. This is where binary heap comes into picture. In a binary heap, in the first level, we'll find out the parent node is greater or lesser than the child node. So the insertion of the element is easy. Inserting element at the proper position takes no more than order of log n. Order of log n is less than order of n. So we can insert easily. Why? You no need to compare with all the elements. Let's look at how this works. They also gave really nice algorithms here. So is it clear so far? I don't want to go beyond this.
Yes.
So the problem what we want to solve is, we want to let's only focus on the min heap for the time being. Okay. So the problem is, we want to take the minimum as quickly as possible. So none of the data structures will allow you. One is normal array. Normal array, you need to traverse all the elements in order to find the minimum. Okay, but if you have sorted array, the problem is insertion. You need to insert at the correct location. Otherwise, next time if I ask you to print elements in a increasing order, the order will change. If you are adding the 225k, the employee with 225k at the end, it will be problem. So you need to insert at the right location, and you need to shuffle the elements. That is a lot of processing, order of n. So even with the same problem with the linked list, you can put the elements in an increasing order, but when you are adding an element, if you're adding at the middle or the beginning, it's okay. But if you're adding at the end, again, you need to check the value with every node and then add it. But if you are having a priority queue, this is a min heap, it is easy. So how? Let's see. Okay.
Suresh, one question.
Yeah, go ahead.
So instead of heap, can we use normal BST which is not having this property heap property?
Yes, normal BST, binary search tree, right?
Yeah.
That's a good idea. So binary search tree, it won't give you the minimum, right? Let's say you have these 3, 10, 15, 25. You got 3, 10, 15, 25. Okay. So how do you want to put these numbers? So 3, 10, 3, 10, 15, 25. If you are putting 3, you need to put 10. You need to put 10 here because greater, right? You need to 15. Again, 15 has to here. You need to put 25. This is the BST of the given values. Correct?
Yeah.
Now if I'm asking you to put an employee with 20 or 30, employee with value 30, you are again going all the way here. Unless you balance. If you are balancing, let's say, if you want to add a value with 30, what happened here? You are already checking with every employee value. Is it greater or less than? Is it greater or less than 30? The value you want to insert is greater or less than 15. If I'm asking you to insert 17, then compare with 3. Let's go right. Compare with 10. Let's go right. Let's go with 15. Now, you need to go 17. Okay. Yeah, you need to, let's say you want to insert 13, not 17. You want to insert 13. Now you will say, okay, 13 is less than 15. Let's go here and put 13 here. So now you are not checking 25. I know, let's say 25 has another 1000 elements. You are not checking all of those. You are only checking 3. You checked with 3, you checked with 10, you checked with 15, and you inserted 13 here. In this case, it's not worst case. It's just order of 3. Just 3 elements you verified. But in the worst case, you need to verify every element. If I ask you to insert 30, you checked every node, because this tree is not balanced. If the tree is balanced, I agree with you, because if the tree is balanced, let's say if you balance this tree by something like this, 15 and 10 here, and then 3 here, and then 25 here, then what happens? You can simply add 30 here. You no need to check with 10 or 3, right? So this is another way. I totally agree with you. So having a binary search tree is good. But the problem here is, with this binary search tree, how can you get the small value? If I ask you, okay, this is binary search tree, give me the small value. What you need to do is you need to take the root and go to the left, and you need to traverse all the way here, and then you have to give, okay, 3 is the small value. So even the retrieval also order of log n, right? Retrieval.
Yeah, correct. Yeah. In the worst case, it will be log n.
Yeah. So if you balanced binary search tree, the insertion also order of log n, and retrieval also order of log n. But in case of heap, retrieval is just order of 1. Just give me the top. Here is the top. You already have the reference to the root, right? Here is the value of the root. Take it. So if you want to find the minimum quickest, very order of 1, without calculating, without doing any processing, you do all the process behind the scenes. When you are adding an element, you do all the process and make the tree ready. Whenever I ask you, give me the small number, You should not do any processing. Just give me the value. So order of 1, just the value of the root, because that is the smallest, right? Min heap. But if you are having this binary search tree, you need to go all the way to the left node, and then you can return the tree 3. Not only that, it's only small. If I ask you next smallest, you need to again traverse the next smallest element is 10, or there could be let's say 5. So as the right node of 3, 5 is there. So next smallest is 5. So you cannot, if it is only one smallest element, you can simply have a smallest element in the tree. You can cache that value. But if I'm asking you, give me the values in a sorted order, then you need to traverse again. So that's why BST is not a great solution for retrieving the small value with order of 1 complexity. That is why the heap came to picture. Okay, is it clear now?
Yes.
Yes.
So now,
Yes,
now
Suresh.
awesome. So now let's inserting the binary heap. Now we got the tree. As I said before, we have the tree like this. 3 is smallest ever. Now you recruited another employee. 3 means, let's say 3K, 3,000, and 5 means 5,000. Let's say you recruited another employee with just $1,000 or 1,000 rupees per month. That will go all the way to the top, right? How can you do that? So we need to find this is the process of insertion. Before inserting an element in the binary heap, we need to validate some of the edge cases. We need to find the empty cell first. Where do you want to insert? First, you need to find the empty cell, and then we need to check if the min and max property of the node is maintained. Let's say, if not maintained, we need to swap the elements. This is the value. This is the case. So you're inserting an element. Let's say you have this tree. Let's take this small tree. I think this is a small one. Yeah, 3, 10, 15. So here is 3, here is 10, and here is 15. And what we have, 25. Okay, so 25 is here. Now, if I'm asking you to, let's say you are inserting an employee with value 30. Okay, I'm inserting an employee with value 30. You can simply put 30 here. We are good. No need to do anything, right? Because it still maintained the heap property 10. It is 10. 10 is smaller than 30. We are good. There is no relation between these two, right? Even if I ask you to insert 24, you can simply insert 24 here. No need to, no problem, because 25 can be on the left, 24 can be here. There is no relation between these two. As long as they are greater than the root, we are good. Now the problem comes into picture when you want to insert a small value than the value which we already have in the tree.
24 should not be there for 10, right? The 24 should
20?
be on 20 on the node of 25.
It can be here, it can be here. What is the problem? So yeah, I totally agree. You can put 24 here, but if you put 24 here, it will break the rule, because always the root value should be less than the children, right?
Okay, only less than, not to the left or not to the right, right?
Yeah,
Only should
yeah,
be less.
exactly. That is what the min heap, right? So min heap, parent node value is less than child node value. That's it. They are not saying left child or right child,
Okay.
right? There is no relation between left and right as well. So now, but if you are putting values in a proper way, you need to fill the first level, you need to fill the second level, you need to fill the third level before going to the fourth level, right? So we don't insert here. Basically, there is a value here. So there are some spaces. There is an empty space here. There's a left node. There is an empty space, one more left node for this, one more empty space here. So there are 3 more empty spaces you can fill before going to the next level, right? So that's why we will put, let's say you want to insert 30, you can simply put 30 here, and once you insert 30, you need to make sure it satisfies the heap condition or not. It is still satisfying because this value is 10 here. So Let me put properly. So this value is 10 here and 3 here. So which is good. If you put 30 here, we are good. But if you put something which is smaller value, you want to insert, let's say you want to insert 1. You want to insert 1. So how to insert 1? 1 means it is smaller than any other element in the tree. By looking here, we can see. But if you have a million elements, you cannot even see, right? So if you are inserting 1, so one needs to go to the top because that's a minimum element, right? If you put, if you should not override 3. 3 is still there. He did not resign. So where do you want to put 3? If you are putting 3 at the last, that will break the problem. That will break the condition. So you need to put a 3 either here or here, and you need to shuffle the elements, right? So how to do that? That shuffling is an algorithm. So what we need to do is we need to put 1 at the end. Initially we will put wherever the empty space is. Usually that is where the empty space, right? So you will put 1 there, and then just manage the roots, manage the root elements. You don't need to shuffle any other elements. Let's look at this. So
Why
here is
can't,
yeah,
sorry, why can't we make one as a parent of three?
1 as a parent of 3, which is really good. That's really good. That's so you're creating a node, and then you can assign the node. This is node dot left equal to 3, node dot left equal to whatever this is beautiful. That's really great solution. Now the answer here is, if we are representing this, let me think. So if you are representing this in a node with left and right, it is easy. But if we are representing in an array,
Yeah.
you're always talking about array. Array is here. Arrays. That's why I explained the array problems before. So 3 is here. This is 0. So you cannot create an element at -1 index. You cannot create an element before 3.
Yes.
But I totally agree with you. If it is in a kind of a root, we can definitely use this. You can just create a root and then assign the 3 there. Yeah, I think that. But the problem here is, let's say you want to insert 2. What do you do? Again, the same problem will come because oh no, not 2. Let's say you want to insert 4. You want to insert 4, and you cannot insert 4 at the last because 4 is less than 10, right? So it should be between 10 and 3, right? You need
Yes.
to insert 4 either here or here. So that's why you need to, this algorithm is okay, but again, that requires the shuffling. So what the main algorithm here is, what we need to do is, we need to find the empty cell, and then we need to check if the min and max property of the node is maintained. If not maintained, we need to swap the elements. So the swapping elements means so here is a min tree, here is a min heap, and we added 1 here. So what we need to do is we need to compare with the parent. Okay, what will happen here is, so swap 1 and 19. So 1 goes here, 19 comes to the down, and then no, 1 is here, 1 and 5. You will compare 1 and 5, swap 1 and 5. So 5 will come here and 1 will come here, and then compare 1 and 3. 1 goes there and 3 goes down. See this. If you want to show both, here is the thing. So see that at the place of 1, 19 came here. In the place of 19, 5 came, and in the place of 5, 3 came, and finally 1 goes there. Basically what happened here is, you're just comparing with parent and swapping. Okay, so now you can ask me, why are we doing? We are doing because you need to maintain the minimum element at the top. And what is the advantage here is, you are not touching any of the nodes here, 17, 25, 100. You're not even checking whatever the value. Even you're not checking with 8, 16, or 60. You don't care because you just inserted at an empty space, and then you are managing to the top, because there is no relation with left or right side nodes, right? I clearly told you the min heap is always a relation with its parents. As long as the relation maintain with the parent, we are good.
Okay, Suresh, are we filling it in the first empty space we are encountering in the
What is
array?
that? What is
Are
that?
we are we filling the new element in the first empty space we are encountering in the array, right?
Exactly, exactly. We are going to insert in the first place in the array. Yeah, first empty space in the array. Yeah. Extract value from the heap. Simple. We can just extract. Extracting basically means removing. Let's say now you have the heap here. Let's say the employee with salary 3,000 resigned from the company. What do you do? Again, the same problem. So if you remove the root completely, the root was eliminated. So what we need to do is we need to put the new element here, right? That new element should be the smaller than any other elements, right? So there is an algorithm for that. What we need to do is we need to put the max number, the last number onto the top of the tree. So by the way, this is called bottom up heapify. There is a word for this. You put the one here and you are shuffling the parents, right? That is called bottom up heapify. So you are heapifying the elements from the bottom all the way to the top. Okay. Similarly, what we need to do is if you are removing the root, if you are removing the minimum value, we need to put the last element at the top and then compare. We need to shuffle the elements. This is called top down heapify. So what we need to do is you put the 100 there, but that is breaking the rule, right? 100 is breaking the rule. What we need to do is we need to find the minimum element. What element goes there? So the minimum element is between 5 and 8 is 5. So the 5 goes to the 100 place and then 100 goes down into the 5th place. Okay. Now here is 100 and 17 and 19. Again, 17 is small. 17 goes to the 100 place and 100 comes to here. Now 100 and 25. So finally 100 goes here and 25 is here. So that's how it is. So if you look at here, if you just remove 3, you need to take 5 there, right? If you take the 5, you need to take some of these 17 here. So same thing here. Basically the if you are removing at the top, right? So by just putting the last element at the top and top down heapify, if you are doing top down heapify, it will automatically put the elements at the right place. See this. So the left, until now the 100 is at the as a right node of this one. Now it became left node and 25 goes up. Why are we doing here is we are not shuffling any of the nodes. We are not touching 8, you are not touching 16. Look at that, right? So rest of the nodes are just, unaltered. You did not touch any of those nodes.
So
That
Suresh,
is,
can we start from any of the bottom node, like maybe 17 or 25 or 19, 16, 60, anyone, or is there any process to know the shortest path, like if one
yeah.
of the path is shortest?
Yes, that is interesting. So, yeah, we can start with any of the nodes, I guess. Let's see if you start with 16. Let's say if you start with 16, what happens is you go 16 there, and then you will compare with 5 and 8, right? And 5 goes there, 16 comes here because 5 is smaller, right? 16 comes in the place of 5. Now you are comparing 16 and 17, 19. That's good actually. Yeah, look at that. So now we maintain that, right? So we no need to do any changes. If the 16 comes here, 17 is at the top and the bottom here, 19 here. So yeah, but this is a usual. This is a kind of, so the algorithm says you need to take the last element and that you need to put it at the top. So I need to find why that is the decision. So the only value you can extract from the heap is the root value. So if you're extracting the only value, you have to extract the root. You cannot extract any children. You cannot extract any children node from the heap when you extract a root from the heap, navigate to the last element in the tree and make it as a root and then adjust the tree. So this is a formula. So you need to take the last element and that make it as a root and then adjust the tree. So that's how we do. So they are explaining all these things, how this works. And so they are also putting the the processing time here. Here is the complexity. Extracting root element is order of 1. Now the size of tree is null, just order of 1. Else get the root, order of 1. Decrement the size of the heap, order of 1. And sort the heap elements, order of log n. Complexity is order of log n, height of the tree. Basically, at any point, the maximum element is, you're right, if you take 16, you're just checking only 3 elements, right? If you take the 16 here, but if you take 100, you're checking all the elements all the way from all 4 levels. So the maximum is order of log n. So because if everything is in an array format, right, how do you know 16 is better? It's not in an array, it's not in a tree format, and it's all in an array format, right? So you don't know which element, which element, taking which element is better, to shuffle the values. You simply take the last value and then put 100 at the top and then reshuffle all the values. That's the worst case is order of log n, right? That is the complexity of the removing element and heapify. And delete entire heap. So if you are deleting entire heap, like order of 1, right, and complexity is order of 1, basically you are keep on deleting first element. Of course you need to heapify, but that's how it will work. Okay, is it clear, everybody, or any questions so far? Oh, we already crossed 9 actually today. Yeah.
Yes. Clear.
Yeah, so now next in the next week we will see how this heapify works, because we just discussed about the concept, how the heap work and how to remove the element, how to add the element. So if it is in an array format, this is the algorithm, right? We have this algorithm here, how to do this heapify, how to shuffle the elements. Very interesting. So once we learn the heap, we'll also learn what are the advantages of heap. There are a lot of questions in the heap. Maybe I will find 1 or 2 interesting questions where we can use the heap to solve the problem. Okay, cool. Yeah, that's it for today. I think I hope everybody liked it. So I'm going to I will send the links to all of these algorithms, what we found, what we discussed today. So whenever you get a chance, please go through those and understand. Yeah, makes sense.
Sure. Thank you, Suresh.
Thank you so much,
Yes,
Suresh.
Suresh.
Yeah, actually, I have one question. There is a document shared in the chat. Uh,
Yeah, I
Yeah.
have given permission to you. Arvind.
okay. So, what is that for actually? Is
Actually, that is the collection of all the problems we discussed so far and the links of
Okay.
the program. And if there is an YouTube link available, I've added it. I'll update it once in a week.
Sure.
Yeah.
Thank you, Karunay.
Yeah, thank you for maintaining Karunya. I think these are all the sessions I gave until now, and also the links to the actual algorithms, and also links to the YouTube yeah, YouTube recordings.
Actually, the thing is, rather than referring to the other people explaining things about these problems, this is our own resource. So it is easy for me to look
Yep.
into it and get things from it. That's why.
Exactly. Thank you for doing. It's really interesting. Yeah. So
Okay.
I will put all of the algorithms in the in a GitHub for sure. As I said, I put everything here in a online GDB website, but I cannot share the entire project. So somehow, so I will put all these algorithms in the GitHub, and I will share. Uh, yeah, the plan is to cover all these algorithms. As I said, we covered so far array, strings, linked list trees, and graphs is the next one. I will list out a couple of interesting how the directed graph, undirected graphs, and there are shortest distance between two elements in the graph. There are a lot of interesting algorithms in the graph. So at least I will find the best ones and the basic ones. I will explain the graphs after trees. And then we also have some of the sorting algorithms. There are 10 types of sorting algorithms I practiced in the past. I will explain those sorting algorithms as well. So that is the plan. Thank you for collecting all those, Karanya. So and if you go to the YouTube, you can everything is in a you can subscribe to that channel. So then it will be easy. So I am already putting everything in a sequence. So in a particular playlist. So if you go back to the channel and there is a playlist where you can play each and every algorithm, and also in the description I am putting the link to the algorithm. See, this is this is not the playlist. How to, maybe if you go to the here, if you go here, yeah, here is the playlist. So if you go to my channel, and you can see all those algorithms in an order. Yeah. And for any of these, you will see the description, and in the description I put the link as well. Or maybe not for this. You can delete any element. So some of these algorithms I think for the latest ones I put the link to the algorithm as well. So here is the algorithm, link to the code. Okay. So when you're watching, you can open the code and look at the algorithm. Cool. I think that's the thing. Cool. I hope everybody liked, and okay, we'll meet next week then. Okay.
Okay. Thank you, Suresh.
Thank you.
Thank you, Suresh. Thank you all. Bye.
Bye, Karni. Bye, Arun.
Bye, bye, Vanilla.
Bye.
Bye all.
Bye.